Okay, welcome PCS members and friends to our today's PCS IBS seminar. It is a great pleasure to have with us Professor Vadim Ohanyan, and I would like to invite our scientific host, Alexei, to introduce our speaker. Please, Alexei.
Thank you, Tilen. So we have today with us Professor Vadim Ohanyan, who will be talking about electric field-induced flat bands in frustrated quantum spin models. And let me give a brief introduction of Vadim. So he graduated from the Yerevan State University, where he received his PhD in 2003. And he then held a number of positions as a postdoc in Leibniz University. And he was also a junior associate at ICTP in Trieste. Presently, he holds 3 joint affiliations at the ICTP, at the Joint Laboratory of Theoretical Physics, ICTP affiliated center in Armenia, Laboratory of Theoretical Physics at the Yerevan State University, and Kendall Synchrotron Research Institute, Laboratory of Theoretical Physics, where he's a senior researcher. And so his research interests are very close to many things that we are doing here at PCS: theoretical condensed matter physics, statistical mechanics, quantum field theory, including integrable models, strongly correlated systems, and quantum theory of magnetism, as you can guess from the title. And so with this, I welcome Vadim to start his talk. So Vadim, the screen is all yours.
Okay, thank you. Thank you, Alexei, for introduction. It's a great pleasure for me to present my talk here on PCS seminar. Okay, let me start. Well, I'm going to tell you today about flat band physics, but maybe they are not the flat bands which many of you know very well. So they are magnonic flat bands. It's flat bands which we can observe in certain magnetic models, the models of the interacting quantum spins. More specifically, I will tell you about how electric field could help us to drive some quantum spin models into flat band regime. A large part of my talk today is based on the following paper, which we did in collaboration with Johannes Richter from University of Magdeburg and Max Planck Institute of Physics of Complex System in Dresden, Jörg Schulenburg, again from Magdeburg, and Jürgen Schnack from University of Bielefeld. As far as my talk is about quantum magnetism, so I think a brief introduction could be very useful. So actually, what is the models of quantum magnetism? Actually, it has 3 important ingredients. So it's a lattice and localized quantum spins in the at the sides of the lattice. The Hamiltonian is given by the exchange interaction between localized spins. Yeah, the spins is a vector which consists of the operators of which are just the generators of SU2. Yeah, and it could be also a term which is called Zeeman-Ter. It's an interaction with external magnetic field. So this is the simplest part, simplest form of the interaction, but due to the influence of the lattice of the other atoms and ions from the lattice, and due to spin orbit interaction, it can be other more complicated terms into the Hamiltonian. For instance, the interaction between spins could be could have axial anisotropy like this, and it also could be so-called antisymmetric exchange or Dzyaloshinskii-Moriya terms. which in general have the following form. Here, brackets are not commutator, it's just a cross product of two spins. Another ingredient in the ground states or SU2 and translational symmetry breaking. So if we don't consider Zeeman terms, yeah, just the exchange interaction, it's SU2 symmetric. And for SU2 symmetric case, the expectation value of spin from arbitrary side is 0. But it could happen that it's not 0, so it can have some structure like this. So non-zero expectation value corresponds to the breaking of continuous SU2 symmetry. Yeah, and the way it depends on the lattice side, yeah, where J is the index of the lattice side, correspond to the breaking of translational symmetry as well. Or in other words, this breaking of SU2 and translational symmetry brings to certain ordered configuration of the spins all over the lattice. So in the simplest form, all spins can have certain direction, which is same for all sides. This ground state is called ferromagnetic. It could be two sublattices which opposite orientation of spins. This situation corresponds to antiferromagnetic configuration or antiferromagnetic ground states. It could be, of course, more complicated structures like ferrimagnetic or ferrimagnetic ground state, where again we have several sublattices, but they don't compensate each other. It could be canted spins. It could be some spiral configuration where this exponential and wave vector is not trivial, and many others. Of course, there is also some exotic disordered but strongly correlated configurations like quantum spin liquids, spin ice, and many others. And third, last but not least, ingredients is the excitation above the ground states. Actually, there's plenty of many different kind of quantum excitations in the form of the quasi-particles above above the different ground states, but one of them is particularly relevant for our purposes. It's the simplest excitation. It's called magnum, and this excitation is relevant for any system. Because for any system, for large enough or strong enough magnetic field, has ferromagnetic ground state as a ferromagnetic state as a ground state. Yeah, and the magnum is the simplest one particle excitation above this ferromagnetic ground state. So the concept of magnum is quite simple. So if we have the ground state which is fully polarized, all spins on sides are pointing to the same direction, yeah, and then we just compose translationally invariant superposition of flipped spins. And this translational invariant superposition of flipped spins is called magnum. Yeah, of course, it has a number of magnetic moment equal to -1. It has quantum momentum, and it has dispersion. It could be several branches for this dispersion. It depends on the structure of the lattice. If we have several sites in the unit cell, so we have several branches. And the flat magnonic band, now it's very straightforward to see that if some branch of the one magnonic excitation has no dependence on crystal momentum, so we have flat magnonic band. Usually, it demands some strict relation between the parameters of the Hamiltonian. But of course, there are different situations, and now in this talk, I am going to tell you to show you how we can affect this condition by additional physical features. Yeah. So as you know, localized state physics has quite long history, coming back to maybe to the work of Anderson about his localization, but magnonic flat band have been discovered only 20 years ago in this paper of Schulenburg, Honecker, Schnack, Richter, and Schmidt. And of course, before that, there were some seminal paper of Tasaki, Mielke and Tasaki, but this model, of course, these works has something to do with magnetism, but still they were the models of the hopping electrons. And the flat bands, as you know, can be found in many systems of different physical origin, like highly frustrated magnets, strongly correlated electronic systems, cold atoms in optical lattices, photonic lattices, in graphene bilayers, and even in quantum Hall state. Okay, so for each flat band, we have some localized magnon states. So actually, for each lattice, there's some restricted area, which we call magnon trap, yeah, and the localized magnon state is just a superposition of flip spin around this trap. So if the regular magnon is a translationally invariant state, here we have just a restricted area of the lattice, and in order this state to be localized, yeah, the coefficients of the superposition and the parameters of Hamiltonian exchange constants should satisfy the following two relations. Here you can see typical examples of, so actually this means that, as you know, the geometry, the topology of lattice is crucial for localized state. Here you can see some examples of one-dimensional models. So, of course, many of them are familiar to you. So this, which we called diamond chain. So please pay your attention. Actually, we in magnetic diamond chain we have additional link, additional horizontal link. Yeah, and here localized magnons are trapped into this two-side dimer. So this model is called orthogonal dimer chain. This is the sawtooth chain, which is going to be the main topic of the main model of my talk. Yeah, some Kagome strips where we can see the 6-side traps, 4-side traps. Some examples of 2D models here with localized magnons, 2D lattices, localized magnons. And the one particular example, which is very interesting, it's Kagome lattice. So you can see here, it's what is special about this model here, you don't need any special restriction for the coupling constants, even if the coupling constant is the same for all bonds, you will have flat magnonic band. Here you can see the cross-section of the Brillouin zone. So the cross-section of the spectrum, 3 branches of the spectrum around this contour is the Brillouin zone, and you see one very flat band. And in construct, and here another interesting feature that there is no special trap for this lattice. You can take any loop, and you can take just superposition of flipped spin with staggered coefficient, and this loop will correspond to localized magnon state. Okay, now very interesting feature. So what actually Sidebinding model has to do with the spin systems? So there is a mapping between the algebra, between algebra of spin operators, yeah, or SU2 generators, and the bosonic creation and annihilation operators. This mapping is called Holstein-Primakov transformation. So as you see, this is highly non-linear mapping, yeah, and an additional constraint should be imposed for the particle numbers. Yeah. And the general principle is very simple. It's a standard technique of working with quantum spin Hamiltonian. So we make Holstein-Primakov transformation, and then we can rewrite the spin Hamiltonian in terms of bosonic modes, yes, of bosons, and of course there will be interacting terms, yeah, as we have square root, but then we can make an expansion of square root, assuming that the number of bosons is small, so we consider just low temperature and low lying excitations when number of bosons is not very high, and then we can make an expansion of the square roots and get some Hamiltonian which is polynomial in bosonic operators. And if we keep only quadratic term, we arrive exactly at the tight binding model. For the case of model with two sublattices, we'll have two types of bosons, and here you can see the Hamiltonian, which is written for the sawtooth chain with three kinds of couplings. So, of course, this is not an exact mapping, because now we just this map can account only for the small part of the Hamiltonian, the sector which is describing one-magnon excitation. And of course, this is also very interesting and useful approach, because now we can handle S, the magnitude of spin, just as a parameter. And currently, we are collaborating with Alexei, yeah, and Andrianov around this stuff. And the work is still in progress. And so now you can see that we have a direct link between spin models and tight binding model if we restrict ourselves only with the one-magnon sector. And of course, if we keep terms of higher order, we will have some interaction between bosons, and then we can use standard many-body perturbation theory, and this is quite standard. Okay, now about another physical ingredient of our work and my talk. It's a magnetoelectric effect. So as I told you, we want to see how electric field can help us to drive the magnetic model into a flat band regime. And electric field can affect it because of magnetoelectric effect. So the magnetoelectric effect, it's actually it's a family of phenomena in matter when electric and magnetic properties can be interrelated. So simply speaking, it's the situation when electric field can affect magnetization of the model and magnetic field can affect dielectric polarization. And in most prominent cases, electric field can induce magnetization just by itself without any magnetic field and vice versa. This is quite hot topic today, yeah, because it has very important applications in many areas, yeah. And here are some recent reviews about magnetoelectricity. And among many microscopic models of magnetoelectric effect, the one is particularly interesting for us because it has some very deep relation with the quantum spin physics, and this model, this mechanism is called KNB, Katsura-Nagaosa-Baladsky, after this seminar paper. And in this paper, they considered one of the typical situation in certain magnetic materials. So when we have two ions of magnetic, two magnetic ions, yeah, and one intermediate p element like oxygen or maybe sulfur between them. And if we have strong crystal splitting, crystal field like octahedral crystal field, which splits the d orbitals of these d metals, and also we have strong spin orbital coupling, and we have model of some hopping electrons around these orbitals. It can be shown that in this case the link, the bond between two metals, can be polarized. And this dielectric polarization proportional to the following expression, when Eij is the unit vector from the one ion to another one, and here we have also cross product of the two spins of this model, of these ions, and thus KNB mechanism links the polarization of the bond with the cross product of the spins at the site of this bond, and the geometry of the lattice, because here we have direction. And this is this polarization has nothing to do with any shift of ions. This is just a shift of electron density. Yeah, and in simplest case, when we have just a linear chain, and we apply KNB formula, KNB equation for the polarization, we have the following expressions. So if we suppose the chain to be along x-axis, the polarization, will be orthogonal to the chain. And if you look at the and this expression, they are exactly the components of the Dzyaloshinskii-Moriya interaction. The interaction which also is present in some magnetic materials due to spin-orbit coupling. And recently there were some papers about one-dimensional models with KNB mechanisms, some interesting exact results, made many models, for instance, with Andreas Klumper, we considered integrable models, and integrable model with KNB mechanism, and presented some exact results about the magnetoelectricity in models, in one-dimensional models. And the next stage, is to consider the chain to be folded, not as a line, and to be folded as a zigzag, and in this case the form of the polarization is different, and it gets some more complicated form. But again, if we consider electric field to lay in the same plane where the lattice lays, so we will have the model when the part which is describing an interaction between polarization of the model and the external electric field has the following form, which again is the Dzyaloshinskii-Moriya term, but which has some staggered part. Okay, and now the rest part of my talk will be about sawtooth chain. Now we would like to consider sawtooth chain with KNB mechanism, with interaction not only between magnetic field and spins, and also between electric field and polarization, which is given by this equation. And so sawtooth chain is a very interesting model. Actually, apparently it was introduced in 1903 by Kubo. So one can say that this is simplest frustrated spin model. So frustration means that we cannot arrange the spins in such a way to minimize all bonds. So being frustrated model, sawtooth chain, nevertheless, has exactly known ground state. Here we have exactly known demirized ground states when this two spins from this part of triangle, from left side or from right side, form a spin singlet. Yeah, and if all spins from all parts of the triangles are in this singlet state, so we have the ground state. Actually, we have twofold degenerate ground state, like right one and left one. And also, this model is also known for the very specific kind of excitation above this ground states. It's kind of magnetic domain wall, quantum domain wall, or quantum solitons or anti-solitons. For instance, we can split the system, and if one part has in right ground state and another part is in the left ground state, so we'll have some localized excitation, actually. Okay, and this picture is typical for the case when all interactions, all coupling constants are the same for all bonds. But beginning from the beginning of this century, actually, yeah, when magnonic flat band has been discovered, one of the paradigmatic model for this magnonic flat band is sawtooth chain. But here we have to introduce a model with the different coupling, J1 for the basal line and J2 for the zigzag. And it's well known that this model has three different flat bands, one magnonic band for if J1 equal 2 times if J2 equal 2 times J1, or J2 equal minus 2 times J1, and even for equal coupling, but when the axial anisotropy parameter in basal line equal to 1/2. And all localized magnons are localized into this free side traps, and here are the expressions for these localized magnon states. In magnetic systems, localized state has very typical fingerprints in microscopic properties. Yeah, so we can just make some measurements, some magnetic measurements, and found some fingerprints of localized state. For instance, in sawtooth chain, yeah. So if we consider these particular localized states, J2 equal to 2 times J1, so here are their spectrum, and exactly at this point, the lower branch became flat, and here are the expressions for the localized state, yeah, and spectrum became the following. So you can see exactly flat lower branch. And if we look into the magnetization curve expectation value of the spins, of the Z component of the spins, and dependence of the value on the magnetic field. So you will see the plateau, intermediate plateau at M equal 1/2. And after that, it would be abrupt jump to saturation band when all spins are polarized. All spins are pointing to the same direction along magnetic field. So this 1/2 plateau actually is the direct consequence of the so-called crystal of magnets, when all possible traps are occupied by one localized magnet. So if you look at this point, you will see that we can manage this situation with the value of magnetic field, because if magnetic field is equal to 4 times J1, this means that the lower branch of one magnon spectrum is degenerate with the ground states. And so if we have situation with n magnons, yeah, the corresponding energy is the following. And now at B equal exactly to to J1, all these configurations are degenerate. And so here we have a crystallized state of localized magnon, and when the magnetic field reaches this saturation value, it jumps immediately to the ground state, to the polarized ground states. This situation allows one to describe the thermodynamics of the model around the saturation field and for low temperature in terms of the fully classical model of covering of the lattice with the trimers. Yeah, and because the major part of thermodynamics are all dynamics of the system here is caused by this arrangement of localized magnons around their lattice. And in this case, partition function for this covering can be calculated exactly, and then one can have exact expressions for thermodynamic quantities like entropy, specific heat, and magnetization. And here you can see the plots. And for low enough temperatures and for especially when the magnetic field is very close to saturation, so these the curves which are obtained from these classical pictures are very close to the exact numerical plots. So this approach is very interesting. It was mainly developed by Oleg Dershkov from Lviv. Okay, here we can see another magnetization plots, numerical curve for exact diagonalization for Kagome two-dimensional lattice, where again using this picture of covering the lattice with the localized magnon, one can obtain the thermodynamics in terms of such classical model. But in contrast with sawtooth chain, here you cannot do some exact counting, because here in case of sawtooth chain, there's no, in case of Kagome lattice, there's no traps, and you should count any loops, including some nested loops like here, but it can be done numerically. And in this recent paper of Honecker, Richter, Schnack, and Vitek, they do this, and again they get very good correspondence with the numerical and numerical quantum diagonalization and this classical picture. Okay, now in what follows, we are going to consider sawtooth chain with three couplings. So for the right part of triangle, left part, and for the basal lines, we all have three different exchange couplings. This model actually is believed to be a very good model of the magnetic material, some natural mineral called ochroite. It's quite nice. And we're going to consider this sawtooth chain with three couplings and with K and B mechanism, which means that each bond will also has dielectric polarization. And if we support an electric field to lay in the same plane where the lattice lays, so we have the following expression for the terms describing interaction between electric field and polarization. So except exchange interaction, yeah, we have to add this part into the Hamiltonian, yeah. And eventually we arrived at the following model. So in most general terms, we have three exchange coupling, three Dzyaloshinskii-Moriya coupling, and we can add to be very, very general, we can add three axial anisotropies. And here, due to K and B mechanism, these parameters of Dzyaloshinskii-Moriya couplings D1, D2, and D3 are not independent. They have the following form E is the magnitude of electric field, phi is the angle between the basal line of the lattice and electric field, and theta is the physical angle of the bond for the lattice. So as I told you, can be mechanism also is geometry dependent. So this physical angle of the model is important. Okay, now here you can see one magnum spectrum, yeah, for this model. So you can see because of Dzyaloshinskii-Moriya, we don't have time reversal symmetry here in the spectrum. And of course, one can analyze spectrum and try to make it flat, but in some cases it's more convenient to do it just analyzing the a possible localized state. Because now, because here we know that the localized magnum should be localized here, and so if we just make an arbitrary superposition of flip spins here and just demand that it should be localized, we arrived at the following and the following condition for the system parameters. Okay, so here we have flat band conditions, and now we have to solve it somehow. So one possible way, yeah, actually they can be solved in general. And for instance, one can exclude rho 2 and express the localized state in the following way. So it's still a little bit unclear because rho is the actually rho by itself is the combination of exchange interaction and the Dzyaloshinskii-Moriya term, but it could be solved also for in terms of J3 and J2. And so this is the possible one of the possible localized magnum states, yeah, here. And here's the value of saturation. It's also interesting to consider the case without the Dzyaloshinskii-Moriya term, and just to see what new can we have, which new situation can we have if we just consider sort of chain with 3 couplings instead of 2. Of course, here the possibilities are more broad, yeah. And here are the general conditions for the flat bands. Yeah, so J1 is equal to this combination of other parameters, and of course all previously known situations are incorporated here. And here we also find very important thing, that the values of actual anisotropy along zigzags are completely irrelevant for the flat band condition. Only value of J of delta 1, the actual anisotropy into basal lines, is important. Okay, now let us see how electric field can help us to drive this system into a flat band regime. Now, if we switch on electric field and suppose K and B mechanism, our parameters of Dzyaloshinskii-Moriya interaction are not arbitrarily, so they're for the following 4, as I told you. And it turns out that only certain direction of electric field, yeah, can help us to drive the system into flat band regime. More precisely, this direction are connected with the symmetry of the lattice. So the one situation where phi is equal to 0, the field is along basal line, and the field is along zigzag, phi equal to theta. So when phi is equal to 0, yeah, and when we take this particular value J3 equal to J2, yeah, and this is important. So here we have to put also J3 equal to J2, and now we see that for arbitrary J1 and J2, we can tune electric field to this value and obtain a flat band. So this is very important because as I told you, for the regular sawtooth chain, you have so we should have very strict constraint between J1 and J2, yes, in order to get flat band. And here we can tune just electric field for our arbitrary value of J1, J2, and delta 1, and we'll obtain a flat band. So this is very interesting results. And even for the uniform coupling, when J1 equal to J2, we can drive the system into flat band state. And the value of saturation field here is a bit lower than in the case without electric field. This is also important. Yeah, and here are the corresponding plot, numerical plot of the magnetization. Yeah, in this case, for the case of delta equal 1, when their interaction is isotropic. And you can see for any value of J2, we can always tune electric field to such a value to get the corresponding flat band situation. So this plateau and one at 1/2, which corresponds to the crystal of magnons, and then jump to saturation. Of course, we can also do it for just abstract Dzyaloshinskii-Moriya interaction when we do not suppose that they are connected with certain values by K&B mechanism. And again, we can find some interesting flat bands like here and localized state. Another case when electric field is parallel to the zigzag line. Again, here we can have flat band, we can tune the electric field, but here again we need some constraint between exchange constant to be fulfilled. Yeah, and again here we have magnetization plateaus and 1/2 and jumps. Okay, again we can do it for the abstract Dzyaloshinskii-Moriya terms and get the following solution. There's nothing special about this solution. And again, as I told you, the crystal of magnons, which corresponds to flat band, brings to the plateaus for magnetization with abrupt jump to saturation. And what is important that in terms of the polarization, we can also see the effect of magnum crystals. Again, we can, if we plot numerically polarization, yeah, for instance, here it's a plot of magneto-electric effect. Yeah? Polarization as a function of magnetic field, magnetization as a function of electric field, and again we we see here the same picture: saturated state and then jump, and again plateau, which is localized state. Yeah, and here again for polarization is the same, and for different values of J2, so we will have different values of magnetic field at which we have this jump, because we have to tune magnetic field. Okay. So I will briefly touch this topic. So actually, if we have this localized states and crystal of magnons, it also brings some additional entropy. And when we have some entropy accumulation in the system, usually at this point we can exploit so-called caloric effect. So we can use magnetization or demagnetization or polarization or depolarization for affecting the system temperature. And the very known magnetocaloric effect or adiabatic demagnetization, it's a very promising method for obtaining low temperatures or for environmentally friendly refrigeration scheme when you use just a magnetic field and magnetic material for refrigeration. But in our model, due to a magnetoelectric coupling and this localized states, we can also use electrocaloric effect, and we can use electric field for effective cooling. And here you can see plot of isotropes, yeah, in each white line is a certain isotrope, and you can see that depending on the electric field, we can reach quite low temperatures here. Okay, and interestingly, we can also solve this flat band constraint for the system with three Dzyaloshinskii-Moriya coupling in very general form. So here for general J1, J2, and J3, we can find D1, D2, and D3. And at these values, we'll have flat band. Of course, they look very cumbersome. We can get a bit simpler expression if we put J2 equal to J3. But this solution is incompatible with the KNB mechanism, because in KNB mechanism, these parameters of Dzyaloshinskii-Moriya interaction are not independent. They are connected with the value of magnitude or an angle of electric field in a very certain way. So this solution is incompatible. So to summarize what we can say about sawtooth chain with the KNB mechanism in general, we have some particular direction of electric field when we can drive the system with arbitrary couplings to flat band regime just by tuning electric field. And now how about some other models? So here is another very popular model of flat bands. It's a diamond chain. Yeah. Again, if we suppose here magnetoelectric coupling according to KNB mechanism, and if we suppose 4 different couplings, yeah, for each bond of one placket, and actually this picture is a bit wrong, because here we suppose these angles to be different. So actually this bond should be shorter or larger than that one. And again here, situation is a bit different, a bit opposite, because it turned out that here for arbitrary values of couplings, you can always choose the angle of electric field which drives the system, and then tune the magnitude, and you will obtain a flat band or localized magnum. And in case of sawtooth chain, we saw that we have only particular values of the angle, and why it's so, it's still not clear for us. And moreover, here, if we cast electric field according to the symmetry of the lattice, like parallel to some bonds, it brings to some complications in forming the flat band, because in this case we need some additional constraints for the exchange interaction parameters and geometry of the system, which is a bit contrary with respect to the sawtooth chain situation. But still, this is quite interesting result that, again, there's always an angle and the magnitude of electric field which can bring the system to the flat band state regime. Yeah, actually, I think we can finish here. So thank you for attention.
Thank you, Professor Ohanyan, for this very interesting seminar. Let us thank Professor Ohanyan. And we are open for questions. perhaps let me start. So if I understand correctly, in both sawtooth and diamond chain that you've shown, the magnonic excitations are obtained via Holstein-Primakov.
No. Here we used just a direct calculation with
tight binding.
Direct calculation with spin operator, spin Hamiltonian. But as far as we work only in one magnum sector, yeah, it has much in common with a tight binding model.
Okay.
So we of course we can use also tight binding model now, which we are doing now with Alexei. Of course, it has some preferences, because when you use spin Hamiltonian exactly, yes, for your calculation, so the magnitude of spin actually matters, yeah, because
yes.
The larger spin you have, the more complicated calculation you have, because you have some anytime when you act with the lowering of S plus or S minus to your state, there's a coefficients which you have to take into account. But using tight binding model, you have just a tight binding model, and this the magnitude of spin is into the coefficients. So in some sense, it could be more easy to do it. But now we use just a spin Hamiltonian, and we compose, because we know beforehand which state could be localized. So we know that the localized magnon is here. So we compose some arbitrary combination, yes, of flip spins, and then we just demand, using this Hamiltonian, that this state must be an eigenstate of the Hamiltonian, and we get some constraint from this demand.
But in this case, you consider spin 1/2, or it doesn't matter?
Yeah. No. It's matter. Everywhere we consider spin 1/2. Yes. For instance, in case of here, in case of sawtooth chain, we know that the magnon should be localized here, on this free side. So we have some arbitrary superposition of flipped spins with arbitrary coefficients, and then if we demand this state is eigenstate of the Hamiltonian, we arrive at these constraints for the parameters of Hamiltonian.
Okay, thank you. Do we have any questions from the audience? Alexei, please go ahead.
Yes, I have two simple questions. So one is, what are the? I mean, I think you're calling this the traps, the magnonic traps. In the flatbed community, that's usually called the compact localized states. So, say in the sawtooth case, it occupies 2 unit cells. So, are there known examples of magnonic flat bands with different sizes of the traps, like single unit cell, or 2 unit cells is the sawtooth? I'm curious if there are examples with single unit cell.
Sorry, my battery is, so I can switch off anytime. So I'm sorry.
Okay.
Well, for some cases, actually, there's a recent paper of Oleg Dershko and I forgot. Okay, and there's a special situation when you can have something like many body localized, yeah, because now here we have a crystal, yes, of the localized state, but to some extent it's just a direct product, yeah, of one body localized state. But to some case, if we And if you place this localized states into your lattice, yes, you can. So the next one you can place only here or here. They can share the same side. So otherwise, we have to speak about many-body localized states. And of course, I know only one paper about that. Yes, it's possible to some very special situation to construct many-body, like the two magnons localized on five adjacent sides.
Mm-hmm. Well, I mean, my question was slightly different, but related indeed, because with this traps occupying a single unit cell, you indeed then can occupy adjacent sides. Okay, yeah, and the next question, I'm actually curious. So in principle, these magnonic flat bands should be approximate, because when you the Sidebinding model is only an approximation when you do the Holstein-Primakov. So I'm curious if you take into account high order terms. They in principle should lift the degeneracy and select a single state. So I think
it seems that we lost our speaker.
The battery decided time to bed.
Okay, so I guess since how the speaker said, it seems that he's out of electricity and it's not coming at this point in time. So I don't think we should wait because I believe we can conclude with the seminar at this point. So let us thank our speaker, although he cannot hear us, but it was a very nice seminar. So let us thank him again. And thank you all for joining. And with this, we conclude our today's seminar. I believe if anyone has other questions for our speaker, I believe he will be available. Just send him an email and you can discuss further there.